This theory deals with the Chonon geometric field, or geometric Chonon field. The basis of the Chonon field is actually a Jewish philosopher named Rabbi Joseph Albo. Rabbi Joseph Albo lived between 1380 and 4044. And he wrote a book which is called the Book of Principles. In the essay 18, it describes measurable time and immeasurable time, two aspects of time. The measurable time quite fits the description of proper time because it depends on direction in space-time, it depends on the trajectory of a specific clock. And the immeasurable time deals with some measurement of time that is done by many trajectories or limits of many trajectories, and therefore it doesn't have any specific direction and is not related to a specific clock. His idea is quite a raw idea. It continued in 1982 with the groundbreaking work of Sam Vaknin that he did for his doctorate dissertation, in which he described a particle that transfers time, and this particle is a wave function, and where this wave function collapses, time is transferred. And the meaning of time is transferred is that space-time become realizable as a physical object. That means that space-time exists only potentially, and it becomes a physical reality where this Chonon particle transfers the time, or where its wave function collapses. But before we continue, we have to discuss about what is matter, or what are material fields. We know that material fields generate gravity. Material fields are described as momentum and energy, or momentum and energy tensor. We would like to give a new description to matter, and the new description is that material fields actually prohibit geodesic motion of tiny clocks. What does that mean? It means that as a particle interacts with a material field, and it interacts in a non-gravitational way, then this particle doesn't go in straight geodesic curve. In Minkowski spacetime, the straight line is the longest time, not the shortest time as we are used to think when we deal with ordinary Riemannian geometry. Actually, it's a Minkowski geometry in which the straight line is the longest line. And there are actually two ways to influence measurement of time. One way is that the trajectory of the clock is bent. That means that it's prohibited from moving along a geodesic curve. Another way is to allow the particle to move along geodesic curve, but the space-time itself is curved. In both cases, the measurement of time between two events along a trajectory of a particle, and these events are actually the collision of this particle with detectors, such that the particle is not destroyed, then the difference between the time measurement between these two events is affected either by gravity or by non-geodesic motion. That if the particle is allowed to move along a geodesic curve, it will measure more time. If space-time is not curved, also it will measure more time. This is how both gravity and other fields influence the measurement of time. Okay, so we say that a straight line actually measures local maximum of proper time between two events along a trajectory by a material clock. And we said that this is unlike ordinary geometry, in which geodesic curves measure local length minimum, the shortest path, but here we measure the maximal path actually, because it's a Minkowski geometry. And here's a summary of how can we influence the measurement of time. We can let the particle move along geodesic curves, but curve space-time itself by gravity, or we can bend the curve and preventing it from being geodesic, as other interactions do. That means other interactions means non-gravitational interactions. But what is the covariant way to describe this idea? The covariant way is to describe acceleration, actually for acceleration. But there is a problem with acceleration. Because an acceleration acceleration describes the bending of a trajectory, but it depends on a specific trajectory. It's a 4 vector that depends on 4 velocity. And we want some description that will be free of a specific trajectory. Eventually, we want to have a Scar-Friedman description. Scar-Friedman description is a matrix, is an anti-symmetric matrix that by multiplication of this matrix with the 4 vector of velocity, we get the vector of acceleration. So if there is a field of acceleration, a field that prohibits geodesic motion, we would like that our final description of such a field will be by this anti-symmetric matrix, and not even by a 4 vector. But we start with some field, and we say here we define a field of time. What does it mean, a field of time? We know that the general theory of relativity prohibits a specific direction of space-time as being a preferable coordinate of time. This is a total contradiction to the principle of relativity. So how can we define such time that does not depend on a specific coordinate? That means that it is not realizable as a coordinate. Okay, so we say that a coordinate of time requires not only magnitude, but also direction. Direction means a unit vector that points to a certain direction in space-time. Okay, and what can we say? An example is that there is a submanifold of space-time, and this submanifold is 3-dimensional, and from each event in space-time we want to draw a curve that connects this event to this submanifold. And by this we can describe actually a scalar field of time. Why is it a scalar field? It is a scalar field and not a specific coordinate, because we can connect between each event to that manifold along different curves. That means the curve that connects the event to the manifold and measures the maximal time that can be measured between such an event and the manifold is not unique. Another thing, that for consistency we would like that loops will be prohibited. Otherwise, if you have closed time-like curves, that we will not have an upper limit to our measurement. But more than that, we would like that this submanifold will be a result of some physics law. That means that we will have an equation, and from this equation there will be more than one solution to such a manifold that can be can serve as a reference manifold or a zero manifold. So maybe we'll make some drawings here, and we'll try to illustrate that in a way that will be understood by the observer of this lecture. Okay, so we would like to what we would like to do is to draw a manifold, and after drawing that manifold we would like to describe a point in space-time in which is connected to that manifold. So we can use this primitive means of doing so. Suppose that we have, let's say that this is a domain in our manifold, and here we have some sub-manifold, and we have an event, and we want to connect between this event with geodesic curves to that manifold, and along each such a geodesic curve we can measure time. Okay, here we have a little clock, and we have another curve that reaches that event. So we see that our zero manifold is connected to an event, and along the geodesic curve we actually we measure a proper time. So this is one example of defining such a submanifold. We would also like to show that the solution to such a manifold is not unique, and this is quite a simple thing to show that. Okay, so we can use this manifold, a new manifold, as a zero manifold, and the solution may not be unique. Another thing is that we don't have a specific direction here, and we also know that if by this trick we set a value to each event in space-time, then we can speak about the gradient of this value. Let's say that the value is p, and we want to talk about the gradient of this p. That means the derivative of p. The derivative of p may be in a direction which is not parallel to the trajectories that connect the event to the manifolds. This is a very important feature of this time field, because it means we cannot say that the gradient of this field p describes any velocity. Okay. What about Big Bang? What about the Big Bang? A Big Bang manifold is quite simple, because unlike de Sitter and anti-de Sitter, we have an event which synchronizes all clocks, and even if we cannot reach this event because it's some sort of a singularity, we can still speak about a limit from each event back to the Big Bang along different curves as an upper limit of measurable time. But there is some question here. Why do we need such field of time? What information is added to space-time by a field of time? What is the information that is included in this field of time which is not included in the geometry of space-time itself or in the metric tensor of space-time? And the answer to that question lies in the definition of non-gravitational interaction. Non-gravitational interaction means that a test particle or clock, a tiny clock, is not allowed to move along geodesic curves. Okay, so this assertion is very important, because without these assertions there is no justification for defining a field of time, because it doesn't add any information to space-time or to the metric tensor. Okay. Another thing is that the norm of velocity is constant. It's c squared. That's a 4 velocity. So if we want to use the norm of velocity and to take its derivatives, the derivatives will be 0. So the gradient, as it appears, of square velocity is actually 0. If we talk about parallel geodesic curves of, let's say, dust, then we want to say what happens to the velocity. The gradient of this velocity will be 0. We want some square norm which will have a gradient which is not 0. We'll see why in the continuation of this lecture. So the Minkowski pseudo norm is very important. It's most important that the gradient will not be constant, unlike the Minkowski pseudo norm of velocity, which is constant. Another thing that we will eventually, as we mentioned before, we would like to also use this norm of a field, our field of time, to get an anti-symmetric matrix, which will describe acceleration by multiplying this matrix with velocity. We will get a 4 vector of acceleration. So we say that actually material fields prohibit geodesic motion, and material fields are of energy, and also an electric field is a form of energy. But that means that if matter is simply described by fields that prohibit geodesic motion, that geodesic motion is also prohibited in an electrostatic field. How can that be possible? If there is a neutral particle in an electric field, and there is no dielectrophoresis, that means that the gradient of the square norm of the electric field is constant. How is it possible that something will be accelerated? Some particle that doesn't have an electric charge. And the question becomes sharper if you ask if there is such a phenomenon, then how is it possible that it was not discovered until today? This question can be partially answered. We will see that we have an assessment of 8.61 centimeters per square second in a very intense field of 1 megavolts along 1 millimeter. It's such a strong field that it will pull particles out of the vacuum, actually. So it will be very difficult to measure such an acceleration. Very, very small acceleration. And another phenomenon that we will see is that charge also generates gravity. So if you want to isolate the geodesic prohibition of clocks, we will also have to take into account another effect which is not anticipated by ordinary physics, which is that charge generates gravity that is not predicted by concurrent physics. That means that the energy momentum tensor does not predict this gravity. Okay, so if you have 1 megavolts over 1 millimeters, we would have less than 0.01 Gs. That means that such a phenomenon is very difficult to detect. Okay. Okay, what about zero charge? We have theory. How will we describe zero charge? And zero charge also characterizes the Majorana fields from Majorana's equation, Spinor equation. we will see the charge unexpectedly emerges out of the Euler-Lagrange equations of our action. And actually, charge will appear as a divergence of a curvature vector, of this acceleration vector, a vector perpendicular to the gradient of our time field. And that means that if the gradient of the time field bends, that means that every particle that passes through this field also bends. It is not allowed to move along the geodesic curve as long as this particle can measure proper time. That means that if it's not a photon, if it doesn't travel at the speed of light, it measures positive proper time, and then by slowing it down, it will measure less time. That's one of the aspects of what is a field of time. We will denote this vector by u. Usually u denotes a unit vector. In our case, it's not a unit vector; it will be an acceleration vector, and it can also be an imaginary complex vector. One interpretation, as we shall see, of a Majorana field is that the acceleration vector is fully imaginary, and then if you add it to the u star, then you get actually 0. But this is not necessary, and it's not even considered in the paper as compulsory. Actually, I personally believe that a fully imaginary curvature vector is not physically possible. And my personal belief is that u star plus u is different than 0. I will also refer to error corrections of the paper that was already published in the Physical Science International Journal. These are very small errors, but I'm a perfectionist and prefer that these errors will be fixed. Okay, so there was a paper, and in addition to the paper, there is also a corrigendum. There is a very important part in the corrigendum. It's not an error correction, it's just an addition to the paper, which shows the conservation laws. That means that the vanishing of the divergence of a tensor, of the tensor that replaces the energy momentum tensor. It's very important to show that these calculations are correct, and this thing was done in the corrigendum. You can also find an updated paper. You can look for electrogravity via geometric Coulomb field in academia, or in script D under EYTAN_IL. Okay, now I would like to talk about the acceleration in the vicinity of a charge. I told you that the charge generates actually two fields, and these two fields are not predicted by ordinary physics. One of these fields is a prohibition on geodesic motion. The prohibition on geodesic motion is this part. Actually, it's the sigma k epsilon 0 divided by 2, and this multiplied by the charge divided by 4 pi epsilon 0 dr squared. Actually, it's a Newtonian limit. It's not a covariant way to write it down. There is also a Newtonian limit which describes the gravity, actually what I call the electrogravity, and these two effects add together, and they have to be taken into an account. There was something wrong in the paper in this, because it's a peripheral calculation that is not very important, so I didn't pay too much attention to it. It's not a main part of the theory. Most of the theory is written in a covariant way, and Newtonian limits were not very interesting for me. So this is what was written in the paper, and this is the correct calculation. There was some errors, which I think if instead of divided by 2, it was divided by sigma, but nevertheless there was this mistake. So this term is the correct term. And also there is another correction in the corrigendum. If you see here G mu nu, the divergence of G mu nu by mu here. So this mu was missing. This mu was missing. The upper mu was missing in the paper, in the middle term here. The big G mu nu, semicolon and mu. Okay. Okay. So these are some more corrections. There is also a correction which is already included in the corrigendum, which is that there is a matrix which is anti-symmetric, that A mu nu equals minus A nu mu, and not minus A mu nu. So the indices were transposed. Okay, we continue, and we start concentrating on the meaning of this theory. Okay. We need now to describe the curvature of a scalar field. And by this curvature we will describe the acceleration. In the last lecture we talked about a field of time. And this field of time is denoted by P. And P mu, or P lambda, is the derivative of this field of time. That means that P lambda is the derivative of P by x lambda, by the coordinate x lambda. Okay. So now we describe also the derivative of P lambda by an arc length. This arc length, this t is not time, it's the arc length along along the trajectory, which is or not trajectory, but on the integral curve that is formed by P lambda. And P lambda itself is not a velocity, it's a gradient. But we can say after all we can say that this t is some sort of time measured along these integral curves. If we walk along these integral curves with the velocity which is a normalized vector, but P itself, P lambda, is not a normalized vector. So this derivative depends also here. It depends on the derivative of P by a coordinate, okay? And this is the Christoffel symbol. Otherwise, this derivative will not be covariant. And what we have here is the description of the integral curves. That means that we move parallel to P lambda. And here it's written as this semicolon is actually the covariant derivative. And we say that that x gamma or x other upper index derived by t is a normalized vector. Another thing is that P is a conserving field. We thought that P is a scalar, so we can change the indices in that way. We can transpose the indices, and we can write this. You can actually develop the term of the norm of P and prove this. This formula is trivial. Here's the norm. The norm is described here. Okay. we would like to measure the curvature along the integral curves. So actually what we prove here is some sort of a theorem in ordinary differential geometry. The question is that we have a scalar field, we have the gradient of the scalar field, and we want to measure the curvature of the gradient of the scalar field. So it's an ordinary question in differential geometry. There is nothing special about this operator. And here there is a proof, okay? It's a very important thing that the curvature is calculated along the normalized vectors. Here we take this the gradient of p, and we normalize it by the norm, and then we take the derivative by the arc length along the integral curves, which are formed by p lambda. If you look at that drawing, then the green arrow is the p lambda, and we would like to calculate a curvature vector which is perpendicular in Minkowski terms to the to p lambda, and we have the curve itself. This is the curve that is generated by p lambda, by the derivative of p by x lambda. And we continue here. So we take this thing, we develop it according to this definition, and of course we would like that dx gamma or dxr by dt is a normalized vector according to the way that curvature is calculated in differential geometry. And we come up with this term here. The quarter comes from half if you take the derivative of 1 divided by the square root of pk upper pk lower, then you have pk upper lower to the power 3 divided by 2, and then there is a term 2. If you have two such terms, then you get a quarter. So it's quite straightforward, and we find a perpendicular curvature vector. This is the perpendicular curvature vector. This is this blue arrow, and here it's in terms of norm. Okay, p lambda is norm to the power of 2. In most of the paper it's called z, just marked by letter z instead of writing norm to the power of 2. And here the calculation continues. Here it tells why it's like that, and we find this curvature square equals to this term. Dot means that there is a derivative by an arc length t, and eventually we reach this this term for the square curvature. Of course, we use this important clue which says that the x gamma or r divided by dt is a unit vector. That's what it means, that we move along integral curves, and eventually we get this term which is the square curvature. Here it's written again. This curvature vector can be defined also if we have complex p, but then we will have to have an upper star p and then lower non-star p, and then the opposite. So the term for a complex scalar field p is a bit more complex, but in general it's not difficult to understand the theory here. So again, let's just repeat that it can be given as an exercise in differential geometry to prove that the second power of curvature of the gradient of p, which is called p lambda, to prove that the curvature of p lambda of this field here, to prove that the curvature of p lambda is the second power of the curvature is this term here. It's nothing more than an exercise. Okay. So we continue to the second paper which has formulas on it. Just to summarize what we have here in this paper, in this page, is just a description of a curvature vector. You probably see how it is easy to prove that the curvature vector is perpendicular to the gradient, because if we take in Einstein's convention, we take the covariant PM, that means that the M is upper, and we multiply this with PM, then we have the gradient of the square norm by M, then multiplied by PM upper, and we have also here PM upper. PM upper is like the norm here, so instead of having the power of 2, the power of 2 becomes power of 1, and then all this term becomes 0. So we see that UM is indeed perpendicular to PM upper. And we will use this term, it's very important, because we will use this term to describe the non-geodesic motion, or actually the prohibition of geodesic motion by tiny clocks, which is very important in this theory. Okay, we'll continue here. Now, anyone who wants to get a better impression or a more detailed description of how this theory is developed can read the paper. The paper is called the ElectroGravity via Geometric Honon Field. There is in academia edu you can find it, and you can also find it in ScriptD, and then also in Physical Science International Journal. Here what we want to do is to describe the Zwiskar and Yaakov Friedman matrix, and we would also like to show the degrees of freedom in this theory when the prohibition of geodesic motion is described by the Zwiskar and Yaakov Friedman matrix. So here we describe A mu nu equals to this term here, and you can easily check that if it's defined by P nu upper, or in the complex case by P nu upper star, then because U nu multiply P nu upper is 0, then this is the term that is left, and so if you multiply it by P nu upper star divided by the root of z, z is n square. I told before that in the paper z is used instead of n square. And as if you look at the previous paper, then this the norm square is replaced by z. Okay, so the norm to the power of 1 actually is it's the root of z. It's a more convenient notation that is used. So it's easy to show that that this matrix is actually identical to this matrix here. Okay, and that it equals to that up to a sign, because if you take the derivative, you see there is a minus sign here. So the P mu comma nu, which is an ordinary derivative, it's not a covariant, it's an ordinary derivative, minus p nu comma nu, p nu p mu comma nu minus p nu comma mu equals 0. So the only terms that do not cancel out are actually the this z mu and z nu, but there is a change of sign here, so we have to be careful about this change of sign. Okay, we continue here. That most important is that is this description here, and it's actually it can be described by forms, by the wedge product of forms. It's an antisymmetric result. It's an antisymmetric matrix. Of course, you can also add here some gauge field that vanishes, because if this gauge field is a conserving field, then it vanishes. I'm not sure it has an important meaning in physics. There are other gauge fields that are much more significant than this gauge field that is described here. Okay. Okay, if p mu is imaginary, it's written so is u mu. Well, it's not necessarily true. This thing is not necessarily true, but there are other ways to get an imaginary u mu. Even more interesting ways that are not expected. This is one of the things that was fixed in a new corrigendum. We can continue here. This is a term which is called zero charge. We will see why it's called zero charge, and we will better discuss it. Now, it's very important that if we write it, if we write this term in that way, with using the wedge product from the exterior algebra, then we get the Godbillon-Weil class, Godbillon-Weil cohomologies class. It's a very deep subject. The Godbillon-Weil class describes the foliations, or form of the foliations which are perpendicular to p mu in this case, p mu or p lambda. And you can also see material about the Rib cohomology class, which is described by this curvature vector. The Rib cohomology class is even more important than the Godbillon-Weil class, because it describes the development of the foliations which are perpendicular to p mu, and it can describe whether these foliations expand in an exponential rate, for instance. So it has a lot to do with cosmic expansion. Another thing we would like to discuss is the Reinhardt-Wood metric formula that tries to explicitly calculate this Rib cohomology class, but here we bypass the Reinhardt-Wood metric formula by writing this term here, term 17 in the paper, and it's more related to this TimeField p, and we take the gradient of p, we get p mu. So an extra material that should be read by the person who observes this lecture is an extra material is about foliations, Godbillon-Weil class, and Rib cohomology class. So it's very important to know about this. Just I want to go backwards a little bit. Okay, we have here something that we should see. Not here. Another thing that we should understand here. Okay, we continue here. And one thing that we discuss here is the Euler-Lagrange equations, which, for a matter of simplicity, we choose P which is not complex to make our life easier. So our life becomes easier because we don't take the complex P. And we use Euler-Lagrange equations, and eventually, after showing that Christoffel symbols are the Christoffel symbols, some of them cancel out. Then we get this term. So if we take the variation of u lambda lower and u lambda upper here, or uk upper lower, you take the variation of this L, multiply by the square root of minus g, where g is the determinant of the metric tensor. It's called also the volume element. Then the Euler-Lagrange equations give us this term here. This is very important because it's the curvature vector. The curvature vector is also the curvature vector, upper and lower indices. That means the square norm of the curvature vector here. But what we have here is very surprising, is that we have the divergence of the curvature vector. So if the first term, the derivative by time, so it's called u0. If the first derivative is very small, in appropriate coordinates, that means that we found local coordinates in which we can separate space and time, then it will quite behave like an the divergence of an electric field. And we have here terms which are non-material. What does it mean, non-material? If we say that u mu describes geodesic motion prohibition by some sort of acceleration, it means that u describes trajectory curvature, or the trajectory bands. That means that p mu, p nu, these terms are the gradients of the field of time. They do not directly depend on this curvature, and that's why it's this term is a non-material term. Okay, but here we have something that describes charge. And why is that? You can see in the paper that by some considerations, the acceleration that is expected within the electric field is approximately this term, which is the square root of 4 pi k. K is the constant of gravity. Epsilon 0 is the permittivity of vacuum. And here we say we take the norm of E. So it's actually it's a non-covariant Newtonian term. But it approximates A. And A divided by c square, by the speed of light square, is quite like this term u here. So in order to fully understand these considerations, you should read the paper. And here is another term. Okay, sigma equals 8 pi. And you get that the energy density of an electrostatic field, of a non-covariant classical electrostatic field, can be described like that. Okay, that actually it's a form of that means the a squared divided by sigma k by 8 pi k. K is the constant of gravity, is a form of energy density. So we see there is a connection between this e acceleration and u, where acceleration is acceleration divided by c square, by the speed of light square, is actually u. Okay, we can write it down. Let's write something down here and say that if we have a forward acceleration, so we can say that it equals u. Okay, we continue here. Okay, in the previous picture we took the we calculated the Euler-Lagrange equations by the metric tensor, and we got this beautiful term in which we have something that behaves like matter and a term that behaves like charge multiplied the term that doesn't behave like matter. Okay, we would like to describe the Euler-Lagrange equations by Jimmy New of this term L multiplied by the square root of the determinant of the metric tensor, which is called the volume element, and it is part of the final gravity equation. So here we have this development here, and eventually we get that term. Now in that term we have the curvature vector, the norm of the curvature vector to the power of 2. And this part behaves like matter, but this term is different. First we have the divergence of u, and it behaves like charge if the first term of u, the first dimension, means u0 is close to 0, and this description is possible if we have a separation of space of time and space and time. If you have in local coordinates g01, g02, and g03 near 0. So if separation in this local coordinate system, we can say that the first term of u is very small. So in that case, this uk upper lower behaves like the divergence of an electric field. Now these p mu p nu are not like the curvature. So if we say that the curvature is a description of matter, then we have a non-material term here. One thing we see here is that the relation between acceleration divided by c square and the curvature vector, which is very important. It is discussed in the paper. Here we see the calculation of acceleration from the norm of an ordinary electric field. It is done here, of course, in the non-covariant classical limits. So obviously it's an abomination for someone who comes from general relativity, but even Einstein himself used the Newtonian limit as an indicator, so we can use it here too. The divergence of u is quite similar up to a constant to the divergence of the non-relativistic, non-covariant classical limit of the electric field, and it has a very important significance because it means that even charge can generate gravity, and much more powerful gravity than the gravity which is predicted by general relativity or by any quantum theory. We need a lot of charge to do that, but we need something like plus minus 20 coulombs over 1 meters per cubic meter to achieve a field which can overcome the field of the Earth and create a warp drive. It's not the subject of this lecture here, because we would be drifted to talk about technology. I will only say one small remark, that the Biffeld-Brown asymmetrical capacitors do not accumulate enough charge to generate a measurable effect, a measurable thrust effect. So all these small capacitors, which are picofarad or up to 10 picofarads with 50 kilovolts, are not anticipated to generate a thrust which is more than one tenth of a micronewton. And that means that with ordinary capacitors, it's impossible to observe any warp drive. It's a waste of time. There are other ways to do that. We will not discuss it here. One technique that is not described here is that in the development of these equations, a derivative of a vector is described as a covariant derivative of the vector, and by subtraction of the Christoffel symbols that are missing with their proper sign. So it's a way to turn a derivative into a covariant derivative plus terms which are not covariant. And obviously these non-covariant terms, they vanish in the equations. I do not go into it in these terms because it's quite tiring, but it's a technique that was used here. More or less, this is what I wanted to convey in this part of the lecture. And now we want to do the same, but we want to take the variation by the Euler-Lagrange equations by p nu. I'm sorry. And that means that if this equation is 0, then the variation is also 0. The variation by p mu is also 0. And this equation can be written like that. After some development, you get this term. Here you have the divergence. It's the non-material term. This is very interesting. This term is interesting. It's the gradient of the square norm multiplied by p mu divided by this square norm to the power of 2. And we would like to understand what we can do with these two equations. That means we have, this is one equation from calculus of variation that we get, the vanishing of the variation, and we get also this equation, that this thing is also 0 here. It means that eventually this thing becomes 0 too. Okay. So we would like to see in the future what does it mean. One thing that it means that it's easy to show that from these two equations we get that the divergence of this tensor equals 0. So it requires some technical maneuvers with tensors, and also this thing that the curvature vector is perpendicular to the gradient of p, and eventually we reach this this term is equal 0, and because this term is equal 0, it means that the divergence of this tensor is actually 0. Okay, you can see. Okay, so this actually, this describes a conservation law. And we would expect it because otherwise it would mean that we have some sort of a mistake in the development of the Euler-Lagrange equations, because the divergence of Einstein tensor is also 0. The divergence of this, which is the divergence of this tensor, is 0. So this is why we would expect the divergence of this tensor is also 0. Okay, we would like to speak about zero charge. So here is the acceleration matrix, actually the singular part of the acceleration matrix. We remember that it can be complemented into a regular matrix by adding another matrix which is called B, and it's developed here. Okay, our terms for zero charge is that the divergence of the vector u will be 0, but we would like to see it in full terms. That means that u can be also complex, and if u is complex, then we have something interesting. Okay, because if u is complex, then instead of taking uk semicolon k, we'll take uk semicolon k plus u star k semicolon k. That means that if it is fully imaginary, this term will be 0. Okay, it will be replaced by sum of two terms. Here it's written here. Okay, this equation. This is the norm of u, and also because we changed the order of the star operator. But where is the divergence? Well, we'll take the divergence of u here. Okay, so here this thing is actually, it's 2 times the divergence of u, and here it's written explicitly. We write it down. Write the divergence. All this is the divergence term, and we eventually find out that 4 times this term equals this. And note that we multiply our terms with an anti-symmetric matrix. So whatever is symmetric will vanish. Okay, so here, let's see what we have here. This term, it's the norm here. Okay. Just look for the symmetric terms here. Which are the symmetric terms? This is the acceleration matrix multiplied by this, and we have this term here. Okay, what happens is that if we take the derivative, calculate this, the derivatives here. Okay, so if you take p star nu mu, it's a symmetric term, so if we multiply it by an anti-symmetric matrix, it will vanish. So the only terms that will be left are the p star nu, such that the derivative by mu will be of this root of z, where z is the square norm. And this is why we are left with these terms. Okay, either we take the divergence of mu nu here, or we take the derivatives of the root of z. Okay, so this term, actually this is the symmetric term, the p star nu mu is the symmetric term. Multiplied by an anti-symmetric matrix, this term vanishes, and we are left with this term here. Eventually you get this equation, and then you get this equation, which is the condition for zero charge. It means that the divergence of the u vector equals 0. And here it's written in the complex way. It is important to understand the conditions for zero charge, because zero charge is something that exists in Majorana spinor equations, although it's not the same theory. We came to that to these equations from prohibition on geodesic motion and from geometric Chronon field, and not from second quantization of quantum fields. And so our sources for this behavior are geometric, and actually the geometry of trajectories. Okay, we continue here to see how can we actually describe the field P. So one way to describe the field P, instead of in the way we did until now, is to describe it as a sum of event functions. So these are psi are the event functions, and it's most naive implementation of some Vaknin space-time realization as events. It means realization. It means that space-time manifold exists only where you have a collapse of a wave function. This wave function. But it's a naive implementation, because in some Vaknin theory uses spinor functions, spinor wave functions, and not a scalar field. Personally, I'm not sure that spinors are necessary. And some Vaknis used spinors because he wanted to show the asymmetry of time, that you can add different spins, like you add spins of quarks, and get one direction which is positive. But the way we describe time here as a sum of event functions quite reminds of wavelets. Okay, especially this term. It means that psi j, psi k, where k is runs from 1, 2, 3, 4, 5, 6, 7, 8 until infinity. That means that these functions are perpendicular to each other, so they form an orthonormal basis of some Hilbert or pseudo-Hilbert space. And here is the normalization term on space-time. It means that this event, most of the what is called energy of this event is confined to a small area of space-time. That means that more or less we know where the event took place. So it's a very naive, very simple implementation of some Vaknin theory. Of course, it's minimal. We could make much more complex theory, but we're not sure that more complex theory is necessary. It has to be checked. It's a reason for further research. Okay, we continue here, and what we want to show is what is the technology that emanates from our ideas. So first, if you say that this thing is it complies with charge, with electric charge, then not only matter generates gravity, but also charge, and much more than we expect. That means that the gravity that will be generated by charge is much more than expected by ordinary physics. Okay, here we write the electrostatic field in a non-convariant way. I mean, most physicists will not like that we write it that way, and especially not this zero here. But it's, after all, it's an approximation. And what we see here, okay, here we have U is approximated as acceleration field divided by c square, which equals to this term. Okay, it's only an approximation, as you can see here. And it means that this curvature vector behaves like an electric field up to multiplication with by a constant. And here is a calculation of the virtual mass that is generated by charge. Okay, we can go back. I'm sorry. Okay, so this virtual mass is some sort of a relation, a linear relation with with real mass. That means if we put real mass instead of that, we would get gravity. When we look for it in here, oh, here it is. That means that this thing behaves like an energy momentum tensor, then energy momentum stress tensor, and this behaves like mass. So if we want this thing to be assessed like mass too, then we have to use this term sigma k. Sigma here is 8 pi, and by general relativity, there is we know that 8 pi k multiplied t mu divided by c to the power of 4 is the coefficient of the energy momentum tensor. So if you go back here, we derive this term by going back from something that equivalent to energy momentum back to pure curvature, and the way to do that is usually by multiplying by c to the power of 4 divided by 8 pi k. So we go backwards. Where do we have that? Okay. Okay. So what we have here is this equivalent of mass to charge. So 1 coulomb is equivalent to 5.8 multiplied by 10 to the power of 9 kilograms. This is totally unexpected by ordinary physics. That means that if we use charge, we can get gravity, but not only gravity. Look at the sign. It can be also anti-gravity. Okay, but that's not the only field that a charge generates. We described a prohibition on geodesic motion, so a charge also has another field. For instance, a negative charge generates two fields. One of the fields is the acceleration field, which in the case of the electron is attractive. But the gravitational field that is generated by an electron is repulsive. And if you want to make a technology which is based on that, especially warp drive technology, then what counts is only this gravitational property of the electron, because it's the only property which affects the geometry of space-time. Instead, the geodesic motion prohibition does not affect directly the properties of space-time. It affects it by the equation of gravity. That means indirectly. But what happens directly is that the field that is generated by the electron, the gravitational field that is generated by the electron, is an anti-gravity. And that's why we can use negative charge instead of using negative mass. Okay. One thing which is very important is that we may not need to separate real charge. Okay, we can use maybe some properties of photons, especially according to Hans Geertz, that he assumes a deviation from the standard model, in which even photons under certain conditions can be described as a pair of virtual charged particles which oscillate. This is something which is not trivial. It's not the subject of this paper and of this lecture. One thing that we would like to say is, which is very important, because we have this term of gravity, which is unexpected. It's not part of the energy. Part of the energy it's UK upper, UK lower. It's the energy density. And we get something from the Euler-Lagrange equations which we didn't expect. That means it's also in the nucleus, in the atom's nucleus. When we have protons and neutrons, there could be charge distribution which causes warp drive towards the nucleus itself. That means that here we have a new model for the strong force, which does not use gluons, that does not use directly the SU3 symmetries for describing the strong force. So it's another thing that should be weighed by scientists, is whether the strong force is a fundamental force, or is it caused by some microscopic warp drives within the nucleus itself. And it's a very important research that should be conducted. And the same can be said about the weak force. So all the interactions can eventually, the interactions which are not electric, can be actually deduced to electrogravitational effects. So these are possibilities that should not be ignored. One thing here that we want to go back. Okay. How do we, by the way, how do we derive this equation? This is what are the considerations that are behind this? So I leave it as an exercise to the reader. That in order to prevent free fall in a gravitational field, then we need to exert force, okay, or to use an acceleration. So if you sum up the acceleration that is exerted by the ground we stand on, and this summation has to be to counter the gravity, it should equal to the potential energy of gravity by the classical non-covariant limit. So we can start with classical non-covariant limit and calculate this acceleration which is needed to prevent free fall. That means that if we stand on the ground prevents our free fall. We just want to describe the non-covariant limit. What does it mean? Okay. So we start here. We stand on the earth. Suppose we stand on the earth, and the ground prevents us from falling down. Okay. So the ground actually, what it does, it accelerates upwards. If it didn't accelerate upwards, we would fall to the core of the earth. So that means that the material fields that make the ground prevents our free fall, prevent our geodesic motion in gravity field. Geodesic motion in gravity field means free fall. So actually the ground accelerates upwards. So we can look at the ground as fields that accelerate upwards, and sum all these square accelerations. And if we sum all these square accelerations and we say that that's a form of energy, then in the Newtonian and non-covariant limit, which is actually some abomination in terms of physicists that like to well formalize everything according to the covariant principles, then we get this idea that the square acceleration divided by 8 pi k is actually some form of energy density. So we want to show there is a connection between the acceleration that is exerted by the ground and prevents pre-fall and to the energy that is required by these material fields that prevent the geodesic motion. So it's some sorts of a vague way to infer what is the equivalence of energy of a field that prohibits geodesic motion. But there is more to that in the paper, of course. There is some description of a cylinder of an electric field in 4 dimensions. It's a Gauss law that is generalized to 4 dimensions. One thing we would like to say is that these symmetries, the SU2 symmetry that is seen here, and especially if we multiply B mu by a rotation twice, each index is multiplied by a rotation matrix, so it reveals the SU2 degrees of freedom. Was quite a surprise, although now it looks trivial, but when this theory was developed, it was not noticed. The SU2 degrees of freedom of B alpha beta was not observed at first, and it's quite surprising that we do have these symmetries here as gauge fields also. The SU3 is less surprising because it's an immediate result of the Frobenius theorem. It's SU3 because we are not allowed to change the sign of the determinant. Thus is the determinant of a 3 by 3 matrix, and by using these vectors Q1, Q2, and Q3 as a basis. Means it can be a basis, a 3-dimensional basis, and then we can take the determinant of this matrix. Although Q1, Q2, and Q3 are all the 4-dimensional vectors, but they can be reduced to 3 dimensions. And when they are reduced to 3 dimensions, we are not allowed to change the sign of the matrix, the sign of the determinant of the matrix, because it means that we will not be able to talk about 3 volume in that case, because the 3 volume will collapse to a point or to a plane. So that's why we need that the sign of the determinant will not change, and that's why it says SU3. So it's also something that is expected from the Frobenius theorem. The SU2 degrees of freedom is something that was only revealed if we understand that we deal with an acceleration matrix in the formalism which was defined by Zwiskar and Yaakov Friedman in 2012. It's very surprising.